I'm going to talk about two independent samples t-test. In order to do that, I go through an example. I've got two groups of measurements, training and no training. So we want to know whether a self-defense training will increase the self-confidence of women. So 5 participants were given a self-defense training, and another 5 participants were given no self-defense training. And then both of these two groups filled a self-assessment questionnaire about the level of their self-confidence, and these are the scores. Now, we want to test whether there's a difference between these two groups' self-confidence. So, you can see that the null hypothesis, we say let mu1 be the average score for self-confidence of group 1. Then you have to do let mu2 be the average score of self-confidence for group 2, and then in the null hypothesis we say mu1 is equal to mu2, and in the alternative hypothesis we say mu1 is not equal to mu2. So you can see that already the hypotheses are slightly different from one sample t-test or pair t-test. In order to do this analysis, we have to describe each group. So if I do x bar 1 is equal to 15 plus 18 plus 14 plus 17 plus 15 divided by 5. And that will give me 15.8. And then if I want to do standard deviation of the group 1, that would be 15. So S1 squared would be equal to 15 minus 15.8 squared plus 18 minus 15.8 squared plus, it will go to the last one is 15 minus 15.8 squared divided by 5 minus 1. And then we have to get the square root of the variance. So S1 will be equal to 1.64. Now we have to do the same thing we do, becomes equal to 16, and S2 is equal to 2.55. In two independent samples t-test, t is equal to x bar 1 minus x bar 2 minus mu1 minus mu2 divided by standard error of x bar 1 minus x bar 2. So now you can see that you have got this one, you have got this one. This one needs a little bit of work. In this type of test, the comparison distribution is the distribution of x bar 1 minus x bar 2. All right? This would be the comparison distribution. But we have to say what is it. We know that x bar 1 has got a normal distribution. Mean of the distribution is the same as the population mean mu1, and we just put the variance. And x bar 2 has got a normal distribution mu2 and a standard deviation 2 squared divided by n2. Alright? So if we subtract these two distributions from each other, so let's say if I have got one distribution here, the other distribution here, this is mu1, this is mu2. The difference between these two, mu1 minus mu2, will give me a new distribution. The distribution of the difference between the two would be something like this one. So this would be the distribution of the difference scores. Now we don't have these two distributions, but we have the histogram, you can say, of the sample distribution of the one and the other one. When null hypothesis is true and the population mean difference is 0, and samples are not expected to be perfectly accurate, we use a standard error as a measure to how much difference is reasonable to expect between the sample statistic and a population parameter. So the standard error is measuring how close the sample mean difference is to 0, which is equivalent to measuring how much difference there is between the two sample means. In here, the numerator of the t statistic measures, so when we say t is equal to x bar 1 minus x bar 2, measures how much difference actually exists between the two sample means, including any difference that causes by the different treatments. And then the denominator, standard error of x bar 1 minus x bar 2, measures how much difference should exist between the two sample means if there is no treatment effect that causes them to be different. We can do two different methods to do the standard error of x bar 1 minus x bar 2. One is assuming equal variances between the two populations, and the other one assuming unequal variances. So in the next video, I'm going to talk about these two assumptions, and then we move on to do the test and continue with calculations. Thank you.